Hello, my name is Scott Grizzard. This is Calculus 1, Lecture 3A, Infinities, Infinitesimals, and Limits at Infinity. Now, we've already done limits when x goes infinity. So what we really want to focus on is what happens when the y values are going to infinity. The section in the book covers both, but we've already done kind of the x's, and we've done a little bit of the intuition for the y's. But what we want to do today is we want to improve on the intuition. So, note real fast that we're jumping ahead one section in the book and then we're coming back. So the next section in the book is continuity. We're going to kind of jump ahead, do these computational things, and then come back to continuity, which is much more of a concept thing. So last time we talked about writing proofs. We had a definition of polynomials that we've expanded on. We proved that polynomials have the direct substitution property, and then we did a whole bunch of trig proofs. So last time was really about the formal side of math. Today we're going to take a little break. We'll come back to the formal side of math next time when we do continuity. But today what we want to do is we want to talk about some of the less formal sides, the intuition, and some of the stuff you were more used to perhaps in pre-calc with the way that you would learn how to compute something. Based on intuition. So what we're going to do today is we're going to focus on the intuition messing with infinity. And we'll do a formal definition of rational functions. But what we really want to do is we want to focus on a little intuition when it comes to these. So the question is, what do we mean by infinity? And there are a whole lot of answers to this question, right? There are a couple of different answers that you can see. So I can talk about things like the natural numbers are infinite, right? So I have this set called the natural numbers. So I have this set called the natural numbers, and just recall that's 0, 1, 2. Some books include 0, some don't. Doesn't really matter. Blah, 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 blah. And the fact that this set exists is one of the axioms of mathematics, and this is what we call the axiom of infinity. So the fact that there exists a set of infinite size, okay? This set has infinite size. Now, to make it more confusing, there are bigger infinities, right? So the real numbers have the cardinality of the real numbers is a bigger infinity than the cardinality of this natural number thing. So that's one way of thinking about infinity, is about size of things. But that's not really what we're interested in. What we're interested in this class is kind of unbounded with direction. And it should be noted that there are other ways to think about infinity. I could say we could have infinity equals negative infinity, okay? And this is what happens when you do what's called the Riemann sphere. So if I think about the complex numbers, and I think about the complex plane, okay? So I have this complex plane. Here is 0, 0, right? Here is 1, here is I, here is -1, and here is -I. Now, I keep going this way in all directions, and I get numbers such as 1 plus I, which is right here, and so on and so on and so forth. So I can think about this, I can map these out in a large plane. And then what I do is I take infinity, and I make infinity in all directions 1 point. And this is not as crazy as you think it is. And so I take the complex plane, I add infinity, add a point infinity, and then I make the complex plane into a sphere. So now what I've done is I've taken the Riemann, the space of C, and I've taken it and I've added a point infinity, and I've taken the whole plane, and I've made it a sphere. We're adding 1 point to where all these things at infinity meet. Okay? And that's called the Riemann sphere. And that's kind of interesting. So if you're interested in math, you can look up the Riemann sphere, and it gives you some really interesting things. Things like 1 over x has a limit as x goes to 0. It's infinity. And 1 over 0 is well defined. That's infinity. And 1 over infinity is 0. So you can do things like that. And that's one interesting way of viewing numbers. Now, you lose order, right? Because now your real line is a circle, and that's, unpleasant, but you gain something else. So you've lost order the minute you've gone to complex numbers anyway. So in one sense, where you lose an order, you gain other properties that are kind of nice. That's not what we want. What we want, so this is other ways to think about infinity than the way we are in our class. What we want to think about is unbounded with direction. Okay? So just like we had this idea of arbitrarily close, all right, we had for any epsilon. Now what I want to do is I want to have a concept for arbitrarily far away from 0 with a direction, right? So as this is x squared, right? And as x goes to infinity, so here's in the x space, y goes to infinity, the x squared goes to infinity in the y space, right? So I've got this kind of idea that I'm going that way. I'm going up to infinity as I go right to infinity. And likewise, I've got the same concept of negative infinity, right? Here's x goes to infinity, negative x squared, which means that as I go to the right, I go down. So that's a different way of looking at infinity. It's just unbounded, but with direction. Now, it's important that you have direction. For example, x sine x. Now, it goes to 0 here as x goes to 0, but look at what happens when I go to infinity. As I go to infinity here, it's unbounded, but going in both directions. And it's not really unbounded with direction. This never settles, okay? So I'm not settling toward infinity. I'm not settling. Right? It's sort of like the margarita. If you think of the margarita sitting at positive infinity, right? I'm going, there's an infinite number of days I'm too far away from the margarita. Okay? So that's our concept of infinity for this class. Unbounded, but with direction. Okay. Now, the things that we normally run into when dealing with infinity are rational functions, and functions that are rational-ish. So let's go ahead and give a definition for a rational function. Okay, so f is a function if there exist two polynomials p and q where q is not the 0 polynomial or the 0 function. So remember that f of x equals 0, right? The constant function 0 is a polynomial. It's just where all of those coefficients are 0. Now, the problem with f of x equals 0 is it doesn't really have a degree. You can't really, it's a polynomial. We don't want the bottom to be the actual 0 polynomial. That's not to say that the bottom can't have zeros, but we don't want it to be the 0 function, right? So the 0 function is q of x does not equal the 0 function, right? There's some other a, so that there's some other x and some other y, so that xy, so that the y value is not 0. Okay? There's some non-zero y value. So if f of x equals p of x over q of x, then f is what we call a rational function. X cubed over x squared minus 4, x over x squared minus 1, 1 over x, x squared minus 1. I ought to define that. Let's go ahead and do that. I said something complicated, so let's say definition. F of the constant function f of x equals 0 is called the zero function. Okay. So that's the constant function 0. All right. So the 0 function, by the way, is a polynomial. Curiously, the 0 function is both even and odd. If you remember, not the 0 number, but the 0 function, if you remember those definitions from pre-calc about what it meant to be even and what it meant to be odd, the 0 function is actually both, and you can prove that. And you can actually use that fact to prove cool things. But that's just about the 0 function. So if f is a function, and if there exist polynomials p and q, since the q is not the 0 function, so that for all x, f of x equals p of x over q of x, then f is a rational function. And these are your things. And of course, you have nothing else matters for the rationals. And we've already gone over this. Okay. But we want to talk about, first of all, if f is a rational function, then, and q of a does not equal 0, then the limit as x goes to a of p of x over q of x is simply p of a over q of a. So the point is here that f, if rational functions have ds for all a in their domains. Okay, that's what that says. So, for example, here I have the limit as x goes to 1 of x cubed minus 5 over x. Well, this bottom goes to 1, not 0. 1 is in the domain of this function. So I just sub in, and I get 1 cubed minus 5 over 4, and that's negative 1 cubed minus 5 over 1, and that's just equal to negative 4. Okay, so I don't need this complicated, figuring out what's going on. If it's in the domain, if the bottom does not equal 0, just plug on in the numbers. You can plug on in the numbers if the bottom does not equal 0. Now here I'm talking about the bottom being 0 at a point. Here I was talking about the bottom being 0 everywhere. Okay? That's what I mean by the 0 function versus 0 at a point. So there should be a little thing. Let's just prove this little fact, okay? So let's just say this. I want to show if the limit as x goes to a of p of x over q of x equals p of a over q of a whenever q of a does not equal 0. Okay, and the way I'm going to show it, it's actually takes me longer to write the description than it does the proof. But the strategy is break up with the quotient law and ds on the polynomials. And that's basically the proof. There's a detail. I got to fix the details because remember the quotient law requires us to have a particular thing be true. But this is the whole proof in essence. Okay, so, right? The limit as x goes to a of p of x over q of x, okay, equals the quotient law, and I need to specify when I do this, since Q of A does not equal 0. I can do this because Q of A does not equal 0. So the limit as x goes to A of P of x over Q equals the limit as x goes to A of P of x over the limit as x goes to A of Q of x. Now, since both P and Q are polynomials, I can directly substitute on them. So this limit here equals P of A over Q of A. Thus, rational functions have the direct So, thus, rational functions have the direct substitution property whenever Q of A does not equal 0. So it's a very short proof, and that's how you do it. Okay. So now the question is, how do I deal with rational functions where the bottom of A equals 0? Okay. So, first thing up front, check both the left and the right. Okay. If you have something not, okay, that's the first thing. The second thing is you can use a trick called infinitesimals. And this is really intuition. You can prove that you can do these things, but it requires a lot more mathematics than we're going to get into in this class. But it's very intuitive. So let me show you what an infinitesimal looks like. So let's say, think of A minus as the number just to the left of A, and A plus is as the number just to the right of A. So let me give you an example here. Let's look at an example. Okay. Now, the limit as x goes to 0 of 1 over x. What I'm going to think of this is, I'm going to say equals. Okay? Now, you can just write the equal sign if you so desire. But for me, I'm not really going to, this really isn't an equal, because what I'm about to do is not a real number. Okay? I'm going to say 1 over 0 plus. And 1 over 0 plus equals positive infinity. Okay? In fact, if A is greater than 0, okay, A over 0 plus equals infinity. All right? And A over 0 minus equals negative infinity. And if we think about the graph of 1 over x, or 2 over x, or 3 over x, or 4 over x, you get that right away. So that's kind of where the intuition is going. And again, I'm going to say equals. Okay? Now, I have to check both sides, right? So here's another example. The limit as x goes to 0 of 1 over x cubed. Okay? Now, I need to check both sides. The limit as x goes to 0 left of 1 over x, of 1 over 0 x cubed equals 1 over 0 left cubed. Now, if I have a number that is just to the left of 0, so it's just there. If I cube it, it stays to the left of 0. So this right here is going to be 1 over 0 minus, which equals negative infinity. Now, the limit as x goes to 0 from the right of 1 over x cubed equals 1 over 0 plus cubed, which equals, I cube a small positive number, I get another small positive number. Okay, and I'm going to get 1 over 0 plus, which equals infinity. Okay, so now I'm here and I cube a small positive number. So the limit as x goes to 0 of 1 over x cubed does... Okay, and that's a perfectly good way to do this. Let's look at another example here. Here I'm going to do the limit as x goes to 2 of x squared minus 4, x plus 2 over x squared minus 4. Now, you might just say, well, I've got x cubed, x squared minus 4 on the bottom. Why don't I just, the thing? So you can do that. So let's do it that way real fast. If I have the limit as x goes to 2 of x plus 2 over x squared minus 4, that is the same thing as the limit as x goes to 2 of x plus 2 over x plus 2, x minus 2, equals 1 over x minus 2, with the limit sign in front. Okay, so now I check the limit as I go from the left and the right. Okay, so if I have the limit as x goes to 2 from the left of 1 over x minus 2 equals 1 over 2 left minus 2. Now, where is 2 left minus 2? Here is 2, here is 0, here is 2 left. Right? That's not 2 to the negative 1. It's 2 left, right? Here's 2. Here's 2 left right here. Now, if I subtract 2 from 2 left, I'm going to wind up at 0 left. Okay? I'm going to wind up just to the left of 0 because I'm subtracting 2 whole units from 2 left. So this is going to equal 1 over 0 left, and that's negative infinity. Likewise, when I do the limit as x goes to 2 from the right of 1 over x minus 2, I'm going to go equals 1 over 2 plus minus 2. That is going to be just to the right of 0. So I'm going to get 1 over 0 plus, and that equals infinity. Now, if you wind up in a situation where you don't understand what's going on or you get lost, and that's easy to do, here's a tip. Sub in the number. Okay, so let me give you an example. So I could do this. If I got lost, what I would say is that 2 left is not really, but, that's close enough for government work. So now when I take 1.999 minus 2, it's going to be clear that I'm going to wind up with negative 0.0001. Okay? So 2 left minus 2 is about 1.999 minus 2. And that's going to give you 0.0001. Do I have too many zeros? I do. 1, 2, 3, 1, 2. Nope, I was right. Nope, I was wrong. There we go. Okay, so now I'm going to wind up with a number that's just to, and that's a negative number, by the way. So now I wind up with a number that's just to the left of 0. Make some room. There we go. All right, so that's just a trick. If you get stuck, sub in a number, use your calculator. All right, so let's go back to this. Here's a slightly more complicated way to do it. Now, for this one, I totally encourage breaking it up and factoring first. But I want to do this slightly more complicated thing. All right, so the limit here, the limit would not exist, by the way. We noticed that. So limit as x goes to 2 dn of 1 over x minus 2 dne, since the limit from the left since the limit from the left is not the same as the limit from the right. Okay, I could just sub this in, okay? So if I did this by just subbing in, okay, I'd wind up with 2 left. When I did the left-hand side, I'd wind up with 2 left plus 2 over 2 left squared minus 4. Now, 2 left squared minus 4, okay, is 4 left. So this is going to wind up being 4 left over 0 left. This right here is a positive number. 4 left is positive. 0 left is negative. I wind up with negative infinity. Okay. I do the same thing for the right. I wind up with positive infinity. They don't exist. Now, here is a situation where I would have a limit. Okay. I do limit as x goes to 0 for x plus 2 over x squared. Okay. So the limit from the left, when I do the limit from the left, I'm going to wind up with 0 minus plus 2 over 0 minus squared. But 0 minus squared is positive. I took a slightly negative number and I squared it. That gives me a positive number. So this right here is going to be 2 left over 0 right. And remember that 2 left is a positive number, right? This is the number. It's 1 point. You can think of it as 1.9999999. That is positive. Likewise, I've got here 2 right over 0 plus. Again, I get positive infinity. So here the limit does exist and I get infinity in both directions. So here are the tips for infinitesimals. First of all, they don't work for 0 over 0. Okay? 0 over 0 is bad. They only work for a over 0 where a does not equal 0. What I need to do is I need to split the left and right sides. And if I get stuck, try using an actual number. Okay? So I got 0 over 0. More work is needed. You factor, multiply by conjugate, that sort of thing. Here's one where I factored, and I wound up with 1 over x squared, and then it's 1 over 4. So if you get 0 over 0, you have to do more work. Okay? 0 over 0 does not equal 0, does not equal 4, does not equal infinity. 0 over 0 is you need to go back. It's indeterminate. You need to go back and do some more work. If you get infinity over infinity, you need to go back and do some more work. Okay? So, with a little bit of intuition, you can save yourself some heartache. You don't need to do this thing on the WebAssign where you divide through by the highest exponent. You don't need to do all those things. You can just use some intuitive tricks to figure these things out. And those are legal, by the way. You may think I'm like, oh, no, you have to prove it. I'm willing to... A little intuition will go a long way in this course. Some things you need solid, some things you need solid definitions, solid statements so that you can prove things. This isn't one of them. Okay? There's some things where you need bum, 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 bum. Not this. With a little bit of intuition, you can get that. Okay. So what we've gone over today, shorter one for today, is we've gone over what infinity is and how to deal with rational functions. And these infinitesimal tricks for dealing with rational functions. Next time, what we're going to do is we're going to jump back into theory big time, and we're going to do continuity and the intermediate value theorem. Okay, well, that's it for me. Thank you.